Hello guys, I have done um, we are done with question number 1 and 2, and now we are moving on to question number 3. This is February March 2021, paper 4. Okay, so let's get started. So the first question says, please wait. um, okay, it says iodates are compounds that contain the IO3 minus ion, anion. So it is a negative ion, that's why it's an anion. If it had been positive, it would be a cation. Okay, so this is shown. So it has two double bonds, double two double bonds with ion O and one negative ion. Alright. So explain with the reference to the qualitative model of electron pair repulsion why the IO3 minus anion has a pyramidal shape. Okay, so we need to know that how many electrons, valence electron does iodine has. So let's move on to the periodic table. Let's open the periodic table. So how about we open the data booklet? Data booklet, chemistry A levels. Okay. Okay, so where were we? The periodic table, right? Okay. Okay, so over here, what's the, let me see. Okay, so where's iodine? Iodine is 53, but it is in the 7th group, so the number of valence electrons is 7. Okay, so now let's see. So over here, there are two bonds, and over here there are two bonds as well. So 1, 2, 3, 4, and 5 5 bonds are formed with iodine is bonded with, so 5 electrons, sorry, 5 electrons are used. So something is bonded with those 5 electrons, but the 2 electrons over here, they are lone pairs of electron, which means they're not bonded with any element or compound. So that's why it will have a pyramidal shape, because um, lone pairs have the most repulsion. Okay, lone pairs have the most repulsion, and that is why it will be a pyramidal shape. um, how the repulsion goes is, a lone pair has the most repulsion, and then the bond pairs, sorry, and then the bond pair and lone pair, and then the bond pair, bond and lone, and then bond. So bond pair, bond to bond pair has very least repulsion. Okay, so let's check the marking scheme for this question, which says, this is question number 3. So 3 bonding pair centers and 1 lone pair, that's what I said, right? So let's erase this first, and then we'll move on to the next part. Okay, now it says, the reaction of iodine and hot aqueous sodium hydroxide is similar to that of chlorine. Okay, and hot aqueous. Sorry, I scribbled on it, so I needed to underline this. It's hot aqueous and not cold. And sodium iodate NaIO3 is formed as one of the products. Okay, so firstly we know that what are the reactions of chlorine and aqueous sodium hydroxide, be it hot or cold, but over here it's written hot. So what the reaction is, let me write it. So it's NaCl, sorry, chlorine, so it's NaOH, sorry, NaOH plus Cl, and that's 2. Chlorine is a diatomic molecule, so it will exist as a chlorine Cl2 molecule. Alright, which gives us, let me draw an arrow. Where can I find an arrow? Okay, so we draw an arrow and write NaCl plus NaClO3 plus H, so it's NaCl, NaClO3 and H2O. Okay, so that's how what would be the equation for the iodine one, but we need to, do we need to balance it as well? So how I'm not sure if we need to balance it or not, but how it goes by is you need to remember this. So it's 3, 6, 5, 1 over here and 3 H2Os. Let's see if it is balanced. So 3 Na, no, it's the opposite. So it's 6 over here and 3 over here. Alright, so 6 Na and there are 5 and 6 over here. So Na is cancelled. Matlab Na sodiums are balanced. Coming on to chlorine, so what we do is, so it's first we balance any other elements except hydrogen and oxygen. So first we did chlorine, or we can do so first we did sodium, or we can do chlorine. It's up to us. But then after sodium and chlorine, let's finish off with chlorine, and then we'll move on to the next one. Okay, so there's 6 chlorines and 5 and 6 over here, and then we move on to hydrogens and then oxygens. So hydrogens are 6, 3 twos are 6, and 3 and 6 oxygens. So it's 3 over here and 3 over here. So that is balanced. So what we'll write now in this on this line is, so we write 6 NaOH plus I2, so which gives us let me see, so 5 NaI plus Na, so the product over here is given NaIO3 and plus 3 H2O. Alright, so let's check the marking scheme for the correct answer. So that is it, 3I2 plus 6 NaOH, NaI3, and that is it. Okay, now let's move on. Let me erase this. Okay, so now moving on to C part, which says the decomposition of hydrogen peroxide is catalyzed by acidified IO3 minus. Okay, H2O2 reduces, what does reduction mean? So it gains electrons. IO3 minus as shown. Okay, this is the equation which is shown, and the reaction is followed by the oxidation of I2 by H2O2. Okay, so the first reduction takes place, and then oxidation. These are some of the equations given. We'll come back to these later. Use the data to show that the separate reactions of H2O2 with IO3 minus, so H2O2 with IO3 minus and with I2 are, so H2O2 with IO3 minus and H2O2 with I2 are both feasible under standard conditions. In your answer, give the equation for the reaction H2O2 and I2. Okay, so first we mention how this equation is possible, this one. Okay, so it's H2O2 plus 2H, which gives us plus 1.77. Okay, now we need this IO3 minus to be one of the reactants. So these two are reactants, and when we form uh, the equation, the final equation, we need to add 1.7, so we need to subtract 1.77 and 1.19. Why do we do that? So basically, okay, so what happens is, okay, no, so we add 1.77 and plus 1.99, and so over here the reaction would be feasible, right? Because if we subtract 1.77 minus 1.99, it would be positive 0, right? It would be greater than 0. So that means the reaction is feasible. And for this equation H2O2 with I2, what we do is we so okay, so over here what we do is, so basically these are the two reactants, right? So we add 1.77 and 1.19, which would be a feasible reaction because it is greater than 0. But in this reaction what we do is we reverse this reaction. Why? Because this is one of the reactants. So what would be the equation? So this would be reversed. Let me write it down. So the first one remains as it is, and the second one becomes um, half, oh sorry, 0.5. Let me write it as 0.5 I2 plus 3H2O, which gives um, sorry, I am not sure what's happening. Okay, which gives IO3 minus plus 6H and plus 5 electrons. Okay, so that's how it goes. But what we do is, okay, so this is the answer. And so now what we do is, how about we cancel H2O2? Is it common over here? No, it's not. So what about 2H? How about we balance the electrons first? So we multiply this by 5 to make the electrons 10, and in the second equation we multiply this whole with 2 to make these electrons 10. Okay, so electrons are cancelled, right? Because they are on the opposite sides. So one is in the product and one is in the reactants. Reactants cannot cancel each other, and products cannot cancel each other. Okay, so there are 10 H2O now, and 2 3 are 6 H2O over here. So 4 are left over here, but the rest are cancelled. Yes. Okay. Now what about hydrogen? So 10 over here and 12 over here. So we write 2 over here. Okay, so what is the final equation? So it's like um, 5H2O2, sorry, 5H2O2, sorry, H2O2 yes, 5H2O2 plus what's this? So it's I plus I So it's uh, 1 over 2, so it's I2, yes. And which gives us, let me draw the arrow, and over here it's 4H2O, so 4H2O plus IO3 minus and 2H positive. IO3 minus plus 2H positive. Sorry, 2. Okay, let's look at the marking scheme. So okay, so in the the second equation is correct, and 5H2O2 plus I2. Okay, that's how I wrote. And then IO3 minus and H2O2. So okay, let me see. Okay, sorry. So this is the product. We'll use this equation for the first one. So what we do is we reverse this equation, so it becomes minus 0.68 because this is one of the products. And for the other equation, it would be, this would be used. So 1.19 minus 0.68 would be positive, greater than 0 as well. So which means that the reaction is feasible. Okay. Now let's move on to the next question or part. I'm not sure what is it, if it's a new question or not. Okay, so over here it says write the overall equation for the decomposition of H2O2 catalyzed by IO3 minus. So what we do is we take this equation, this one, and the one I just erased. So this equation, right? And we cancel everything out. So over here it is let me, can we copy this? Let me see if I can copy it. Okay, yes we can. Okay, so what we do is, so it's 5H2O2, right? What we do is we cancel them. Okay, but we can't cancel them because they are in the same direction, so they're both in the reactant, so we can't cancel 5H2O and 5H2O. Okay, how about iodine? So we can cancel it, right? So I2 is cancelled with this, and H positive, so 2H positive is also cancelled, and 2IO3 minuses are also cancelled. So what's left is 4H2O, 6H2O, and 5O2. Okay, so what we do is we add 4 and 6 hydrogens, which become 10, and 10 H2O2 over here, but only 5 oxygens. So it becomes 2H2O2. So if we divide this by 5, so we divide the whole equation by 5, so this is divided by 5 as well, and this is divided by 5 as well, so it becomes 2H2O2 gives us 1 O2 plus 2H2O. Okay, and that's the final equation. Let's see. So it's 2H2O, 2H2O, and 1 O2. Okay, and now we'll move on to the next question. I think this is pretty long, and I'll only do one part, or something like that, because it's for 18 marks and I'm not sure we have enough time for this. Okay, so a student collects some data for the reaction of H2O2 with acidified IO3. Okay, order, we have to show the reasoning order with respect to H2O2. Okay, so what we do is we take the concentrations where we take the column, the rows, two rows in which the concentrations for the rest of two are remaining constant, but the concentration for H2O2 is changing. So we can't take these two because it's remaining constant. What about this two? So okay, we can't take this because the concentration of hydrogen is changing. What about this one? So the concentration between these two is changing, these two is same, and this is also same. So when we divide, let's see, so when we divide 0.15 divided by 0.15 divided by 0.1, what do we get? So 0.15 divided by 0.1 is 1.5. Alright. Now when we divide the rate of reaction, so we divide the same thing. So we divide the rates of reaction, respective rates of reaction. So it becomes 8.82 divided by 5.88. We don't add the powers because they have the same powers. All right, but if they had been different, we would have changed the decimal places as well. So 8.82 over 5.88 is 1.5 as well, which means that this is the first order reaction. Why? Because with 1.5 change in with 1.5 times change in concentration of H2O2, the rate also changes by 1.5 times. Okay, so that's why this is the first order reaction. Let's look at the marking scheme. Okay, so first order with respect to H2O2 and change in concentration is 1.5 gives increase rate. Okay, so that's what I told you, right? Coming on to IO3 minus. Okay, so we check in which the IO3's concentration is changing but the rest two are remaining the same. So 0.07 or 0.14, but this is changing, so 0.07 and 0.14, it's changing. So what about this one and this one? 0.05. Okay, so all of these are changing. Okay, so how about what we do is, let's check for hydrogen ions first, because there's no one which is similar, which have two different in both of them. So 0.025 to 0.05, okay, this is the same and this is not the same. How about 0.025 and 0.05? So this is not the same, this is the same. 0.025 with 0.05, this is not the same and this is not the same. Okay, so what we do over here is, let's check for IO3 minus. Okay, so what we do is, so for different concentrations, so we know that this is first order reaction for this one, right? So we'll see that we'll see the one which has these two constant, so hydrogen ion is constant. Okay, so in 0.07 and 0.14 this is not constant, and for the first and the third one it remains constant, right? So how about we divide 0.14 by 0.07? The answer would be 2. Okay, so when we divide these two, so 0.14 by 0.07, the answer comes 2, which means it's increasing 2 times. How about 5 when we divide 5.88 divided by 1.47? 0.47. So it's 4 order reaction, okay? So it's a second order reaction, but we can't figure it out like that because over here it's also increasing 1 time, alright? So the order of reaction for this one is 1, so it doubles, and because of this it quadruples. So this means this is also first order reaction, right? Okay. Now coming on to hydrogens, so we check for, so the both of them are first order, and let me erase it. Okay, so it was like that, right? So how about hydrogen ions concentration? So we see the ones for which only one of the concentrations is remaining constant and one of it is different. So 0.025 and 0.05, this one is changing in this case as well. So when we divide 0.05 by 0.025, what we get is 2. The answer is 2, so that means that the concentration is increasing 2 times, okay? How about when we divide the rates, which are 2.94 divided by 1.47, that's also 2. So that means that since this concentration is also affecting the rate of reaction by so the order of reaction is 1, which means it is increasing the reaction by the same rate as the concentration is being increased. So it is increasing it 2 times. So for over here it's also 2 and over here it's also 2, which means it's a first order reaction. But we know that the first order reaction was this one, for the high H2O2's one, right? So this shows that hydrogen ions reaction do not affect the rate of reaction, because if it had not been H positive in the reaction, it would still have been first order reaction. It would still have been 2 and 2 over here. Okay. No, give me a minute. Okay, so over here, we are increasing it 2 times. This is also increasing 2 times. What when we divide 0.1 by 0.05, that's also 2. It's not 1, it's 2. So that means it is a zero order reaction because hydrogen ion concentration does not affect the rate of reaction. Okay. Now let's erase this thingy and move on. Okay, use your answer to write the rate equation. So how we write the rate equation is uh, let me draw it. Okay, so we write K, which is for the constant, and H2O2 is a first order reaction, so we write power 1, and then it's what was it, IO3. Yes, IO3 minus is also first order reaction. IO3 minus is also a first order reaction, so we add a power 1 over here as well, but it is a zero order reaction for hydrogen ion, so we don't write it in the rate equation because it has no effect on the rate. That's how it goes. Alright. Okay, so from here we'll do it tomorrow, and I hope you understood the lecture. If you did not, you can always comment and I hope I can solve your confusions out. Take care. Bye bye.